Yes,
So,
sir.
Yes, sir.
so that we are not going to discuss here because everybody knows more or less in your 10 plus 2 class. So here we are going to discuss one more important, phenomenon that one can observe when interference occurs. That is Newton's rings. So have you heard about Newton's rings before?
No, sir.
Okay, let's discuss, right? Um, what is that? I mean, Newton's rings. As the name suggests, so this is indeed an experiment which was performed in 1717 by the great scientist, or you can say the philosopher, the Newton. So therefore, it's called Newton's rings. And since it is an experiment, you might be interested to know. So what are the apparatus or the experimental arrangement? And some of you might have already done Newton's rings experiments in your physics lab, right? So and in virtual lab, we'll also perform Newton's rings experiments. Um, by the way, you can hear me, right? Am I audible?
Yes, sir, you
Loud
are
enough?
audible.
yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So everybody, please go to mute mode. Okay, so this is experimental arrangement, and if you open the Newton's rings experimental setup, you will find these components basically. Okay, so the main component, right, or apparatus is a plano-convex lens. You can see here. So this one is the plano-convex lens. Okay. So why it's called a plano-convex lens? Because one surface we have plane, and another side it is in a convex shape. So everybody knows about convex and concave lens, right? When you talk about lenses, basically two important lenses will come in our mind. One is convex, another is concave. So then therefore, I mean, we have focal length, focal point, and so on. So and then at the bottom, that means we have the convex side of this plano-convex lens. We have a glass plate, namely G. So do remember, whenever you are using any notation or symbol, you have to mention them. For example, L stands for plano-convex, G stands for plane glass plate. So these two are important in apparatus, or you can say component in Newton's experiments. Okay, and then in order to get interference, what we have to do? We need to incident coherent sources of light. So therefore, a monochromatic source of light could be used as a coherent source because we have single frequency or single wavelength. The intensity distribution will be clear, and if you use polychromatic, that means many frequencies, the intensity distribution will not be that much sharp. Okay, so S is the monochromatic source of light, and here we have a convex lens, and the convex lens we have put at a focal distance of it from the source. So it means you put the convex lens in a such way that the distance between the convex lens and the point source is the focal length or focal distance of this convex lens. Okay. And why we have arranged it? In order to produce a set of parallel beams the other side of the convex lens. So this is the definition of your focal point or focal length. So if you remember from convex lens working principle, if we incident a beam of light, parallel beam of light, and what we'll get? So they will converge at a point, namely focal point, and this is your focal distance. So it means if you put a point source at the focal point, the other side of this convex lens, you can generate a set of parallel beam. Okay, so that therefore the distance between this convex lens and S is the focal distance or focal length of this convex lens. So as you can see that we can generate set of parallel beams. Okay, and then but our experimental arrangement is here. We need to divert them. So therefore we have a again plain glass plate, right? We should not use a mirror, because if you will use a mirror, the other side will be shielded, the light beam cannot pass. So therefore we use a mirror, and what will happen, since we know that reflection and refraction will occur, so some portion will get reflected and it will travel downward. If the angle between this set of parallel beam, incoming parallel beam, and this plain glass plate, namely B, is roughly 45 degree, then it will reflected vertically, and some portion will get transmitted. So that is not interested. They will get transmitted and they will move away here. So that portion of beam is not interested to us. Okay. So therefore, this thing. So now what will happen? So this beam will travel, downward, and since the angle between this plain glass plate and this, horizontal beam, monochromatic beam, so 45 degrees. So therefore, so the beam which travels downward will incident normally on the plane side of this plano-convex lens. So this means the angle between this is roughly 90 degree. So theta is roughly 90 degree, because this is roughly 45, therefore it is 90 degrees. So therefore it is normal incident, and you can see, right, this solid upward arrows. That means something will happen due to the presence of this plano-convex lens, namely L, and the plain glass plate, which is we put beneath of this plane convex side. So something will happen, and the beam will travel upward, as I have been encircled by this red color, and again it will travel upward. And then since it is a mirror, it can pass through the mirror, and as you can see, I have put this arrows, and then we can visualize here. M stands for a traveling microscope. Okay, and we can observe something through this microscope. So this is actually not fixed, it is traveling, because we can get beams over the surface of this plano-convex lens. So therefore we need to travel it. So this is things that happens inside this Newton's rings experiments, or the Newton's rings apparatus. So is it clear to everybody?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes or no?
Yes, sir.
Okay.
Yes,
Yes.
sir.
So everybody please go to mute mode. So we understand, right, why we are using this source, yes, which kept at a distance cell at a focal length from this convex lens, why it is mounted 45 degree, and how come we could observe something through this traveling microscope. Okay, so now what will happen when you observe through this traveling microscope? We'll find, like circular ring patterns, right? So that will appear alternatively. Dark, bright, dark, bright. Because polychromatically, we are observing these patterns like dark, bright, dark, and bright. And why we have a circular ring, which has circular rings, not only single ring, many rings, which has single center. You can say the concentric rings or circular rings. That means single center. Why? And why it is appearing like this? That we need to discuss. So as I said, in the earlier, the main component of this, Newton's rings experiment is the plano-convex lens and the plain glass plate, which we put beneath the convex side of this plano-convex lens. So let's look, carefully what is happening here. So that I have, enlarged. You can see here, right? So this is the plano-convex lens, and we have a glass plate. So now this is the one of the incoming beams, which has intensity I naught. Okay. So what will happen? Since it is almost normally incident, what will happen? So this beam will travel further without any reflection. As you know, if you have a normal incident, there will be no reflection, only refraction or transmission. So the intensity remain unchanged. So I should tell one more thing. So we know this reflection and transmission and refraction will occur. So in this process, what will happen if you have an incident beam I naught? So let's say it hits in another medium. Let's say glass to water. Let's say air to water or glass. What will happen? So some portion will get reflected and then it will transmitted like this. So now I can say IT transmitted and IR reflected. So the intensity, if the initial incident intensity I naught, IR represents reflected intensity, IT represents transmitted intensity. So so we should have this law, IR plus IT for any angle. Okay. So if we have a normal incident, since there will be no reflected, only transmission, so therefore the intensity remain unchanged. So that I have done here, since it is almost normal incident. So now what will happen when it reaches at the bottom side? That means the curved surface of this plano-convex lens. So it will no longer a normal incident. Okay, you can see this green color, right? So this is the normal, and it is no longer a normal incident. So therefore we'll have a reflection, and that reflection beam is coming here. Okay, and then some portion will get transmitted, and again it will travel in this gap. That means the gap between the top surface of this glass plate and bottom surface of this plano-convex lens. And again, it will get reflected and then transmitted, namely the beam A. So now basically we have two transmitted beam, or you can say the reflected beam, one that reflects from the bottom surface of the plano-convex lens, another that reflects from the top surface of the glass plate, namely E and F. So therefore I have written down a reflected beam from the top surface of air film. Then you might ask question, what is air film? Because the beam E is reflected from the bottom surface of the plano-convex lens, whereas the beam F is due to the reflected beam from the top surface of glass plate. So and if you look here, so in between the bottom surface of the plano-convex lens and top surface of this glass plate, there is nothing. It might be empty. And you can see, so this is the point of contact, namely O. If you move away from this point of contact O, so do remember it is a three-dimensional picture, right? So it is a three-dimensional picture. If you go, any direction on a plane, which normal is perpendicular to the plane glass surface, what we find that the gap between the bottom surface of the plano-convex lens and the top surface glass plate will increases. Okay, am I audible?
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
Okay, please go to mute mode. So it is three-dimensional space. So if you go move on a plane, move away from the center, what will happen? The gap will increase. Okay, so this is basically gap, And if you put some liquid, transparent liquid, so you can call it say liquid film. And if there is a nothing, you could call it air film. So therefore, instead of saying that the beam E is due to the reflection from the bottom surface of plano convex lens, you can say the reflected beam from the top surface of air film, and F is due to reflected beam from the bottom surface of the air film. Okay, so that I have written down. So E is due to reflected beam from the top surface of air film, whereas F is a reflected beam from the bottom surface of air film. If you use some transparent liquid, then you can say, liquid film rather than calling air film. So now,
Sir, one doubt.
yes.
So this E and F will be parallel.
So that I am going to. So this E and F,
Okay.
they will come out or emerge out almost parallelly. How it will be almost parallel? So if it will be normal incident, and it is possible when this the curvature side or the convex side of this plano convex lens is almost flat. If the I'll talk maybe later. So as we know that a curvature is defined by the curvature of radius of curvature. Okay, so it means, so this portion of this curvature must be part of an imaginary sphere because it's a 3 dimensions. Therefore, I'll call it sphere rather than call circle. So this portion must be a part of an imaginary sphere which has certain radius, and that radius is known as radius of curvature of this convex side of plano-convex lens. And if the radius of curvature is very, very large, then this convex side will be almost flat or almost plane. If the radius of curvature, radius of a sphere or circle is very, very large, then you might not observe the curved side of this curvature. The classic example is our Earth. We know it is almost spherical shape, but the radius is huge or very large, so therefore we would not realize that we are actually living in the curved surface. So when the radius of curvature is very, very large, then when you say very, very large, in the context of what, that we'll also discuss. For the time being, we remember, if the radius of the curvature is very, very large, so that case this curvature side of this plano convex lens will be negligible, the curved part will be negligible, so therefore these two beams will emerge out almost parallel. Only that condition. And if you look the plano convex lens that inside this Newton's rings experiments uh, setup, you'll find that is indeed the very large radius of curvature or almost flat. Okay, so in that conditions, this beam E and they will both E and F will come out almost parallelly. And since they will travel simultaneously, and as per the definition of the superposition, that these two beams can superposed, and then the intensity will distribute between minimum and maximum, right? And that might lead to such kind of patterns, bright and dark patterns. So let's see, right? So now we understand this E and F beam, they can superposed. Where this E and F beam will come? So this will come the top surface of the air film and bottom surface of the air film. If you have nothing inside the cap, if you have a transparent liquid, then rather than calling air film, we'll call liquid film. So now, so let's since they can superpose, therefore coherent superposition can occur or interference can occur because we are dealing to light wave. So therefore we have interference, and as for the interference, the intensity will get distributed between minimum and maximum, and that might cause the distribution of this intensity, or the rings will appear bright and dark alternatively. Okay, so let's discuss. We now understand why why the pattern will appear dark and bright alternately? Because when the intensity will be maximum, it will appear as a bright. If the intensity will be minimum, it will appear as a dark. Okay, and then as per the condition for the interference or coherent superposition, if you remember, the delta phi will be 2n pi. So the intensity will be maximum and it will be n pi, intensity will be minimum, 0. So now you can see the pi, 2 pi, 3 pi, 4 pi and so on, they will come appear alternatively. So therefore the maximum and minimum or dark and bright pattern will appear alternatively. But it does not explain why we have concentric circular ring that we are going to discuss. Is this clear so far?
Yes, sir.
Yes, sir.
So okay, so now so let's discuss why we have concentric rings. So as I have already told that if you move away from the center, the point of contact, the gap will increase, right? So the gap will increase. Okay, so let's focus on what is happening at a particular point, namely B. The beam is coming like this. Let me go up. So I have shown only 3 beams, but there are actually many beams that is incidenting on the surface of this plano-convex lens. And since it is 3-dimensional object, so what will happen? We have a circular surface. This plane side of this plano-convex lens is a circular surface, and the beam is incidenting all over the circular surface, not only in one direction. Hello. Yes. Am I audible?
Yes, sir.
Yes, sir. Yes, sir.
So as I said, it is a plane surface. If you look the top, it is actually a circular shape. It's a 3-dimensional, right? You can imagine, right? And therefore, the beam is incidenting throughout this circular surface rather than incidenting in a particular directions. Okay. So now we are picking one of the beams, and let's say that is this one. Let's see what is happening. As I have told, that we'll have 2 beams, they'll get superposed. Okay, so and then when they'll superpose, what will happen? Then it could lead to your maximum intensity or minimum intensity depending on the relative phase difference between this E and A. And by looking this schematic diagram, we can conclude that it would be easier to calculate the relative path difference between these 2 beams rather than the phase difference. Okay, from this geometrical diagram. So once you calculate the path difference between this beam E and F, you can translate to the phase difference. And therefore, if it is 2n pi, then you can conclude that it would be your maximum, therefore a bright spot. If it is n pi, it will satisfy n pi, then it will conclude the intensity will be 0, therefore a dark spot. So do remember I am saying dark spot or bright spot. And so this point B is a distance r from the center. So what is happening at the point B? The same scenario might occur, the same scenario must occur on the surface if you move away at a distance r from the center. So it means, so let me draw. So this one, so this is the point of contact O, and this is B, which are distance small r, from this point of contact. So let's say this is 2 pi. So therefore B leads to your a bright spot. So what is happening at B, and if you move on the circumference of an imaginary circle which is distance r from this point of contact, because do remember it's a three-dimensional object, so then you'll get bright spot. So you'll get bright spot here all over the circumference which is distance r from the point of contact O. So what is happening B? So the same scenario will occur if you move away distance r from this center point of contact. And if B leads to your bright spot, so all these points that falls on the circumference which has radius r will lead to a bright spot, and if you join them you'll get a bright ring. So therefore the ring structure appears due to the symmetric nature, that we can say symmetry, because if you move at a distance r from the point of contact, the scenario will remain same. So therefore we can say that due to the symmetric around the point O, therefore what is happening B, it will exactly happen the distance r from this point of contact, or an imaginary circle which is at a distance r from the point of contact. And if it leads to let's say pi, then we'll have a dark spot. So therefore we'll have a dark ring. And as I said, pi, 2 pi, 3 pi, 4 pi, it will appear alternatively, and hence we have maximum and minimum, or dark and bright rings will appear alternatively. So in short, the ring-like structure appears due to the symmetric nature of the air film around the point of contact O, and the alternative dark and bright rings appear because it is the consequence of the interference. That means the 2n pi bright spot, n pi dark spot. So now we understand why we have alternative dark and bright rings appear from the Newton's rings. Is it clear to everybody?
Yes, sir.
Yes, sir.
Yes, sir.
So now we understand, right? So why we have concentric bright and dark rings. Then the question here is why the central one should be dark, and what would be the mathematical expressions. That means, can we derive mathematical expression that will explain whatever we said, right? A to n pi or n pi. Yes, we can do that. So now we have to figure out what are variables or parameters associated with this Newton's ring experiments. We have to convert this physical problem to mathematical problem. That we have already done, like simple harmonic oscillator case, damped harmonic oscillator case, coupled oscillator case, and so on. So if you look here, we have I naught, the intensity. It is due to we can say the intensity is not the you can say the wavelength or frequency or amplitude. That is amplitude related to the intensity, one of the parameters. And then you can say, as I said, that this air film is symmetric around the point of contact of the from its center, around its center. And if you move out, you can see that we have two parameters, namely R, and you can say the thickness of the air film T. And you can see the thickness of the air film, it is not constant. It varies as you move away from the point of contact or the center of the air film. And this radius of the Newton's rings and the thickness of the air film, there are two variables or parameter, but they are not independent parameters or variable. It means T depends on R and R depends on T. Therefore, you can consider any one of them as independent parameter rather than considering two. So now we have one independent parameters. So, but how we can link them R to T, that we'll see. And then, as you know, that the bright and dark, rings, they appear by satisfying these couple of conditions, delta phi 2 n by n pi. As I told you, it is much easier to calculate path difference rather than the relative phase difference. First, we have to calculate how we can link this path difference by 2 n pi or n pi. And then next, how we can convert, or how we can find a relation between this radius of the Newton's rings, namely R, and the thickness of the air film, namely T. These are two objectives we need to do through mathematical approach. Is this clear to everybody?
Sir, that
Yes, sir.
n, so that
Yes.
n pi would be 2n plus 1 pi, no? For dark band.
I mean, 2n plus, it's like, pi, 3 pi, you can put, and then I have not written down n, right? If I put n equal
Yes,
to,
sir.
let's say, 0, 1, 2, 3, and so on. Here n equal to 0, 1, 2, 3, and so on. Sorry. 3, 5, 7. Or if you like, 0, 1, 2, 3, 4, you are true. It should be 2n plus 1 pi. Okay. It depends on how you choose n.
Yes, sir.
Okay, thank you. So, but the aim is clear, right? We need to get a relation between the radius of the Newton rings, namely R, and T, the thickness of the air film, and then how we convert this path difference or link this path difference to this 2n pi or 2n plus 1 pi, which are conditions for maximum and minimum brightness. So whatever I have said, I have written down here. Let me read it out. So these reflected beams C and F will superpose coherently to produce either dark and bright spots depending on the thickness of air film T. Because if the air film thickness T varies, and that related to the relative phase difference. Due to symmetric nature of air film around O, these spots, either dark or bright, will appear as rings that we have already discussed in great detail. So these rings will also appear alternatively, which can be viewed by traveling microscope. So one can see two parameters are associated with the Newton's rings. One is small r and T. So these two are not independent, as I said. And in principle, one can show that the thickness of the air film is related to the radius of the Newton's rings R by this relation, where capital R is the radius of curvature of the plano-convex lens that I have already talked about. That means the plane, the curvature part is, the curvature portion of this plano-convex lens is a part of an imaginary sphere which has radius capital R. And for bright spot, this relation, and dark spot, this relation, as one of you have told, right? So it should be 2n plus 1. If we would like to write 0 integers including 0. And when we talk about rings, right, then what would be the value of n? We should either consider the positive side of the integer or the negative side of the integer, not both. Why? Because the ring is symmetric around. This will be your positive x-axis. This will be your negative x-axis. Okay. And when you say, n equal to plus minus 1, it indicates the direction. And since we are talking about rings rather than the spot, so therefore either we should consider the positive side of the integer or negative side of the integer including zeros. But we should not consider the both side. Okay, because we are dealing with the ring rather than spot. And as you know, the relation between the path and phase difference can be expressed by this, expression. delta pi phase difference between two reflected beam, namely E and F, and path difference between them. So so delta x, so therefore in terms of path difference, for bright rings, this condition, dark ring, this condition. So do remember, we don't have negative sign, as I said, because the rings are symmetric around the center of the air film, or the point of contact between plano-convex lens and plane glass plane. So now, so we need to calculate the delta x. And from this geometrical configuration, you can see that since everything is happening in a very small angle, as I said, the radius of curvature is very large. And in fact, the radius of curvature is very large in comparison to the thickness of this air film or the wavelength of the incident beam. Okay, so therefore you can see from this schematic diagram that the approximate extra path traveled by the beam F compared than E is this much. The distance traveled by this beam F through this air film, the 2 times distance, you can approximate, since it is 90° and it is very flat surface, close to flat surface. So therefore everything is a small angle. So you can say the twice that the beam F travels twice extra path in travels twice inside the air film compared than the beam E. This twice is equal to 2 times the thickness of the air film 2T. So that I have written down here. So the delta x is roughly equal to 2T because the F beam travels twice through air film. Okay, so therefore 2T equal to n pi for bright and 2T equal to n plus half lambda for darkening. So now we convert that the relation between the thickness of the air film in terms of, or the bright rings or dark rings mathematical expression in terms of the thickness of the air film. But there are one more optical phenomena one can observe called total internal reflection that we'll discuss in polarization chapter. So for the time you should remember here, and we'll derive mathematical expression there. So it is called the phase reversal phenomena from the bottom surface of the lens compare than the E beam. So do remember the E beam reflected from the top surface of the inside the air film. That subgroup extra phase pi. And as I said, we'll derive in the polarization chapter. So therefore, if we include that on the top of this 2T due to the phase reversals delta x path, and that leads to 2T plus lambda over T. Because the extra path due to the phase reversal will be lambda over 2 pi and phase reversal pi, which is lambda over 2. So rather than saying 2T equal to n lambda or 2T equal to n plus half lambda, what we can say, due to the phase reversal, 2T plus lambda over T equal to n lambda for bright ring. And 2T plus lambda T equal to n plus for the bright and dark rings in terms of the wavelength of the coherent source, namely lambda. So this represents conditions for bright and dark rings in terms of thickness of the air film and the wavelength of the coherent source of light. So is this clear to everybody? Only mathematics, nothing else.
Yes,
Am I
sir.
audible?
Yes.
Yes,
Yes, sir.
So now we derive mathematical expression bright and dark rings, and when we put n equal to 0, the expression of bright and dark rings, what will happen that in dark ring expression t leads to 0 when we put n equal to 0. So t equal to 0, what does it indicate? It indicates that the center of the air film, that means the the portion that around the center of the point of contact between plano-convex lens and glass plate. So that's the condition for the darkening. Hence, at center we must have darkening. So now we understood why at center we have darkening. From this, as we can derive from this mathematical expression. So now we know at center we have a darkening. So, then the next question is, we need to convert this relation in terms of the radius of the Newton's rings rather than the thickness of the air film. And as I said, we have this relation. So as I said, I have asked that one for homework. So you need to derive. So derive it. And in fact, you'll find this in your assignment. This will be one of your problems in your assignments, which I have not posted yet. Probably I'll post very soon. So by using that relation, and you can convert this, the thickness of the air film in terms of Newton's rings radius. And here we have diameter of the Newton's rings in terms of the wavelength, radius of curvature, and what is n? N represents the order of the Newton's rings. So do remember, so if you move away center, we have rings, right? So this represents the order or position of the rings, either it's a first, second, third, fourth, and so on. That n represents that position or the order of the rings. Okay. So since the n represents the order of a ring, it is appropriate to put a subscript with this diameter d subscript n that represents the diameter of the nth ring, right? And this is condition for bright ring. So the diameter of the nth ring should satisfy this equation. So similarly, one can derive the diameter of nth dark ring, which will satisfy this relation. And what you can observe from these two mathematical expression, that the diameter of any ring is directly proportional to square root of the wavelength of the coherent source, directly proportional to square root of the radius of curvature, and of course this order of the ring. So in short, or finally, that we derive the mathematical expression of the Newton's rings. That means we can get the diameter of either nth ring, nth dark or bright ring, if you know the wavelength of the coherent source of light lambda and the radius of curvature of the plano-convex lens capital R. Okay. So so that's all about Newton's rings. And whatever we have done by assuming air film, that means nothing inside nothing inside the gap. That means the bottom of the plano-convex lens and the top of the plain glass plate. And as I said, if we put a transparent liquid which has a refractive index mu right? A transparent liquid with a refractive index mu, and we can also determine the refractive index of the transparent liquid by using this relation. And you need to derive, and as you can see, right? So these three belong to in your assignment problems. Okay. So the first one, as I said, you need to derive the relation between the thickness of the air film T and the radius, radius of the Newton's rings smaller and the radius of curvature of the plano-convex lens. In fact, you should derive this relation, and since the thickness of the air film is much smaller than the radius of curvature of the plano-convex lens, so therefore what we can write, we can approximate this 2RT minus T square equal to 2RT, and therefore we have this relation. Okay, and the second thing is, by using this mathematical expressions, you need to derive this, the wavelength of the monochromatic, the coherent source of light that used for interference. D subscript n plus p stands for the diameter of n plus pth ring. Dn stands for diameter of nth ring, and you can determine by measuring the diameter of n plus pth beam and nth beam, and knowing the radius of curvature, you can determine the wavelength of the unknown source of light. And similarly, you should perform the same experiment by using some liquid medium in the index of the meteor. So first you need to measure the diameter of n plus pth ring. A superscript A stands for air, and the nth ring, and you repeat same experiment using the transparent liquid. You measure the same set of ring and do these things, we'll get the refractive index of the transparent liquid that used in the Newton's rings experiment. So by using Newton's ring experiments, you can determine the wavelength of unknown source of light, which must be coherent, and then the refractive index of the unknown transparent liquid. And you need to derive this to mathematical expression. And in your virtual lab, probably in third or fourth experiments, you have to perform these experiments. What you have to do, you need to measure the diameter of the ring, nth order rings, for example 20th ring or 20 plus 4th ring, 24th ring or 25th ring, and you measure the wavelength as well as the refractive index. So therefore it is essential to derive the relation between the diameter of Newton's rings, wavelength, and radius of curvature, and indeed we derived it. So that's so this is all about Newton's rings. And so any question?
Excuse me, sir.
Yes.
Sir, is the traveling microscope different from a normal simple microscope?
No. But those who have done Newton's rings experiments, so you will find a screw is attached, right? If you rotate it, it will travel, back and forth. So how many of you have done Newton's rings experiments in physics lab? Because we have conducted, one physical lab. Some of you must have performed Newton's rings experiments. So who are they? Okay, yes. So Mr. Reddy has done it. If you remember, there will be a screw, right? You have to rotate it, and it will travel automatically. Yes or no, Mr. Reddy?
Yes, sir.
Okay. And don't worry, those who have not seen, these things in physics lab, in virtual lab, you will also do that thing, okay? But it will.
Sir, in previous class you mentioned about a book, right, by Mr. Ajay Ghatak, something like that. Sir, can you share the PDF, because since we are not in the campus, we don't have access to the library and books.
Okay, let me first say one thing. In principle, it is illegal to share the whole book, but I'll share the portion of the books. For
Sir,
example,
this chapter, you
The
can share the
particular
PDF.
chapter only, not the whole book.
okay, that I'll share. Okay, don't worry, that I will share. Okay, and as I said, whatever I am teaching, it's not only in a particular book. I have borrowed from many online resources. So which I might have forgotten. But anyway, the Ajay Ghatak book is very good book for optics, and everybody should follow it. So anyway, so I'll share the Newton ring portion of the Ajay Ghatak books.
Thank you, sir.
So any more question? I hope everybody understood, right?
Yes, sir.
Yes, sir.
Yes, sir.
Yes,
The
sir.
first thing is when translate this physical problem, some mathematical working problem, and then you have to do it. So that exactly we have been doing, not only for Newton's ring, even if the simple harmonic oscillator, damped forced, even if coupled oscillator systems. Okay, so now we studied great detail interference through Newton's rings, and in the next class we'll talk about another important phenomenon produced by light, namely diffraction. And after that, we'll talk about polarization. So I think we should stop here and we'll meet the next class to discuss about diffraction. So bye everyone.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.